Thanks very much. So this is based on some work, mostly based on some work in progress with David Simmons Duffin and John Cardy. And also, I might have maybe sometime at the end, I'm not sure, I could talk about large N disorder, but that's only if I have some more time. And that would be based on some paper that already appeared a month ago. Also, I would be very happy for questions and comments. This is some work in progress, and some things might not be complete yet or completely clear. Okay, so let me start from some motivation for what kind of physics problems this can arise. So let's consider something like the Ising model in d dimensions. So ordinarily, if you have some configuration of spins, so let's say you have some spin configuration, so the probability for the spin configuration would be given by the usual Boltzmann factor. So it would be given by e to the minus beta, and then there will be j, sum over sigma I, sigma j, over nearest neighbor interactions, and that would be divided by the partition function. And so in that way you could compute the probability for some given spin configuration. Now, experimentally, it's known that there is some critical beta. So there is some critical beta, which is called the Curie temperature, where this system develops a second order phase transition. And there are long range correlations between spins that are far apart. And this is described by a conformal field theory in d dimensions, which may be mean field theory or it may be an interacting conformal field theory. So this is a well-known story. But experimentally speaking, it seems that in many situations, one has to consider the effects of some external fields which cannot be experimentally turned off. So there may be various external fields like temperature perturbations or magnetic fields, external magnetic fields, that are hard to control. And the presence of these external perturbations may or may not be innocuous. So sometimes the existence of tiny random magnetic fields, external magnetic fields, can change the nature of the phase transition altogether. So in the usual situation, we would say that suppose there is some magnetic field, some external magnetic field, Hi, so it would be different at each location. Then we would just change the probability by adding an additional term that looks like Hi sigma I. And then Z is some function of the Hi. Okay? So that would be the probability for measuring some spin configuration when the external magnetic field is given and set. But to model these experimental situations where the external magnetic field is not quite known, we can imagine that the Hi are actually random variables. So they could be really small, but they're still random variables with some very small, let's say, the Gaussian distribution. So one can model these random variables by saying that this, for example, that magnetic fields at different points are completely independent of each other. So the experimental setup. So you model this uncertainty in the magnetic field by saying that at each location, the variable Hi is distributed in a Gaussian fashion. So we just say that Hi, Hj is distributed in some Gaussian fashion with some coefficient that we call c squared. And that on average, at every site, the average magnetic field still vanishes. But there is a small Gaussian distribution, and the higher moments of this variable Hi are given by the weak theorem. So it's a perfectly Gaussian variable for simplicity. So you could think about this kind of situation, and then the probability, this is called disorder, a quenched disorder. So the probability of the disordered system of finding some spin configuration sigma I is now given by an integral over that probability against this kind of randomness. So this is defined to be an integral over the probability of finding the system with some spin sigma I with some given Hi against a Gaussian function, h squared over 2c squared, where this is integrated over space. So this would be the disordered probability of finding the system with some sigma I. And that would still be a function of the temperature. Okay, so there is some dependence on the temperature beta. And one could now ask lots of questions about this kind of systems. Is there a critical temperature? Is there still a Curie temperature? Are the properties of the phase transition the same as in the unperturbed system? Are the critical exponents the same? Maybe there is no phase transition at all. So there could be several scenarios. Let me maybe outline 3 possible scenarios that could take place. And I'll discuss a system in which one of them takes place. And we'll try to do some computations. So by the way, even though this looks like a simple modification of the underlying quantum field theory, it's not. Because there is a denominator that depends on h. So it's not just like taking a quantum field theory and adding some auxiliary variable that appears in a Gaussian fashion. Then you could integrate it out and use ordinary quantum field theory ideas. Here, because of the denominator, you can't integrate out h very easily. Is that clear? So this is not a standard pass integral. You can't pass to the continuum very easily. Okay, so the first thing that could happen, which is the most benign, is that the second order phase transition remains and it's unaffected. So the second order phase transition is unaffected. So the critical exponents are the same. The critical temperature would be maybe the same, maybe slightly shifted. But that would mean that this kind of uncertainty in some external variables is not pernicious to the phase transition itself. Another extreme is that the second order phase transition, or let's say that the ordered phase. So the high temperature phase, just a general comment, the high temperature phase wouldn't care much about these external fields, because at high temperature everything is dominated by thermal fluctuations, and some slight uncertainty in some external fields won't do much if C is sufficiently small. So for temperatures that are very, very high, the disordered phase, the usual disordered, what people usually call the disordered high temperature phase, would not change. But the ordered phase, which kicks in at low temperatures, could, for example, disappear or be very extremely modified. So ordered phase could disappear or it could be modified. So that's another scenario. The last logical possibility that I want to mention is that there is a second order phase transition and there is an ordered phase, but they're different. So the second order phase transition comes with new critical exponents. So there is a second order phase transition, but the critical exponents are not the same. So there could be different critical exponents. So these are some logical possibilities, and it's of course of great experimental interest to know the effects of this kind of random fields, because people are trying to measure critical exponents and heat capacities and things like that. And in fact, the relevance of these random magnetic fields is what makes experiments in the Ising model, the 3D Ising model, very hard. This is one of the reasons that these experiments are very hard, because as I'll mention now, the presence of these random magnetic fields for the Ising model seems very, very important. So it changes the nature of the phase transition very violently. Okay, so you could consider a random magnetic fields, but you could also consider random temperature. So you could also consider a random temperature. What does it mean to have random temperature? What it means technically is that you take this coupling J that appears in the Ising model, you promote it to a matrix Jij, which has support only for nearest neighbors, and that you assume to be some Gaussian variable with mean J and some Gaussian distribution with some strengths C squared. And that has the interpretation of changing that has the interpretation that in your sample the temperature cannot be quite tuned to be the Curie temperature everywhere homogeneously, but there are slight fluctuations around the Curie temperature. And that's because in the mean field description, in the continuum description, of the theory, small changes in the temperature map to the coefficient of the energy operator epsilon of x. So you could imagine that the operator whose coefficient or external field is random is the coefficient of epsilon of x. If you turn the coefficient of sigma of x into a random variable, that would be a random magnetic field, which is what I described for now. Now let me tell you some phenomenology. So this is now going to be a list of theoretical and experimental results in this field. It's by far not exhaustive. It's just a few items that I find interesting. So let me just list a few items that people have measured or proven theoretically. So the first thing is that I'm going to first discuss mean field theory. So this is theory. Okay. So let's take d-dimensional mean field theory. So if you have the mean field theory would consist of some scalar field sigma of x, such that this field is free. So the Lagrangian is just del sigma, and there are no interactions in the dimensions. So for this guy, if you make the operator, for this guy random magnetic field, so if you have random magnetic field, meaning that the coefficient of sigma of x in the Lagrangian, which is like a tadpole, is a random variable. So the effect of that on the system is solvable. It's free field theory. So what the random magnetic field does is, if d is smaller or equal to 4, the second order phase transition completely disappears. And you could say that the mean field theory disappears. It doesn't make sense. So this is like the Mermin-Wagner-Coleman theorem in condensed matter and particle physics, which says that two-dimensional free scalar fields don't exist. What this says is that free scalar fields with a random tadpole don't exist below 4 dimensions. So it pushes the critical dimension by 2. So the second order phase transition doesn't exist. And in fact, the dynamics of the system at low temperatures is very complicated. It's dominated by interesting domain rules and many things like that. So second order doesn't exist. So the order phase completely disappears. Okay, this is one solid result. If d is bigger than 4, then the random magnetic field doesn't do anything. The properties of the critical point are the same as mean field theory. So for d bigger than 4, it's innocuous. Okay, these are some phenological results about mean field theory.
So when you say a second phase, I just realized that free field theory doesn't have a transition. You're saying this is the low energy physics of the
of some model. Imagine some metal or something which is described by mean field theory.
Yes.
If the corresponding external field that couples to sigma of x were to be a random variable, then the ordered phase would have disappeared. Or you could just state it as a result about conformal field theories. If you take a conformal field theory and make the tadpole into a random variable, then this conformal field theory ceases to make sense. It has growing correlations at long distances, so the large volume limit doesn't exist. That's the same as the Coleman theorem. So it's pushed by 2 relative to the Coleman theorem. Now you could also consider random temperature. This is again in quotation marks because that depends on the precise realization of this critical point. So by random temperature, let me just mean that the coefficient of sigma squared x is a random variable. So in that case, most of the time, the system would be kind of benign. The ordered phase won't disappear. So in general, in this case, you could solve the model exactly. There are new critical exponents, but the phase transition doesn't disappear. Okay. Okay, this is mean field theory. Let's talk now about the Ising model. So now I'm talking about the classical Ising model, where the spin is just a binary variable. And in the continuum, of course, you can promote it into a continuous variable. So let's talk about the d-dimensional Ising model. So the phenomenology of this is quite different because there is an interaction term. First of all, the first thing that you can ask is what happens if there is a random magnetic field. So that's a subject of a lot of controversy. Let me just tell you a few facts that are well established. So if d is equal to 2, then the second order phase transition disappears. So the second order phase transition disappears. So the ordered phase disappears. This is the classical computation of von Sager. Now with a random magnetic field, and it can be shown that the ordered phase of von Sager disappears. So the phase transition disappears. Now, what about d equals 3? This is more interesting, and here much less is known. I mean, the properties of the ordered phase are not well known. I think most people believe that there are new critical exponents, and there's still a phase transition. And in fact, you could say that this has been proven, but the properties of these new critical exponents and the properties of the ordered phase are mysterious. So nobody really knows what's the correct low energy, low temperature description of the system. It might be some infinitely coupled. What people sometimes say is that it's an infinitely coupled model, but I don't think that much is known about it, unless somebody wants to correct me. Now, what I will consider is.
I'd be tempted to correct you. I think the ordered phase is reasonably understood in the random field Ising model in 3 dimensions. The critical point, I would agree with you. But,
yeah. So the new critical
phase,
exponent.
It is an ordered phase.
There is an ordered phase. I agree.
It has conventional properties, equilibrium properties.
Right.
The dynamics is much more non-trivial.
Yeah, and also the critical point itself is.
The critical point is.
Is said to be at infinite coupling, whatever this might mean.
0 temperature.
Yeah. So I think that this is pretty mysterious still. It would be nice to shed light on the properties of this phase transition. Now, for the random temperature, I think that the behavior is somehow more benign. For the random temperature case, let's start from d equals 2. So in d equals 2, it's innocuous, so it's irrelevant. And I'll also prove that momentarily. In d equals 2, it's irrelevant, and it has been measured experimentally to be irrelevant. So random magnetic fields in 2 dimensions decay logarithmically as you go to long distances, and I'll explain that in a few seconds. So there is a logarithmic decay. It's like a marginally irrelevant operator in the language of quantum field theory. There is a log decay of the strengths of these random magnetic fields.
Random temperature. Random temperature.
Right. That's for random that's for random temperature. I might have said something else.
Right.
Yeah. So there is a logarithmic decay of this fluctuations in the temperature, effective fluctuations in the temperature. What it means mathematically is that this coefficient C, this is the strength of the Gaussian distribution around the pure fixed point, and that parameter, you can think about it as evolving with the RG. So evolving with the scale in which you probe the system. So when I say that it's irrelevant, what I mean is that the effective C-squared at long distances goes to 0. Okay. So there is a logarithmic decay of the strengths of these fluctuations in d equals 2, and you basically recover the von-Sager computation. So you recover all the critical exponents that are known for ages, which are, as you know, 1, delta equals 1, and 1 over 8. Now, for d equals 3, there are new critical exponents. And they're extremely well measured. Well, that might be a stretch. They're measured to between 1 and 5%, depending on the critical exponent that you have in mind. So, let me give you an example. The heat capacity exponent of the pure Ising model is known to be 0.11. Now, people have measured the critical exponent, the heat capacity exponent for this disordered Ising model, which I'll sometimes call DIM, and that is given by -10. So the critical exponents do change somewhat, and there are tables, and people have measured all of those things, and it's an interesting theoretical challenge to try to compute them. So what have people been doing? So the most prevalent approach to this problem, it seems to be the most prevalent, at least in this community, was the Epsilon expansion. So people have been trying to expand the properties of this disordered Ising model using this exactly soluble. Well, they're not exactly soluble, but at least in 4 dimensions, it's approximately soluble via the Epsilon expansion.
You might want to mention there's a rigorous bound on alpha.
Right. The rigorous in 1 dimension, d equals 1 or.
Well, in general, when the fixed point exists,
right.
Alpha should be negative.
Oh yes. There are indeed rigorous results that say that the heat capacity exponents have to be negative. I'll prove that in some setup. It will be a consequence of something that I'll do soon, but it's known to be a rigorous result. So the most prevalent approach to this problem has been the Epsilon expansion that starts in 4 dimensions and tries to shoot at 3 dimensions. But in fact, these computations do not work as well as the Epsilon expansion that Wilson and Fisher have devised for the pure Ising model. And the reason is that there is an interesting singularity in the Epsilon expansion. So in fact, the expansion does not look like an expansion in epsilon, but in square root of epsilon, because of a singularity in the beta functions. Now, this has far-reaching consequences for the precision and viability of this method. People have gone up to 5 or 6 loops in the epsilon expansion of the disordered Ising model, but nobody has been able to reproduce very well experimental results. So, and as far as I can say, this has been the most prevalent approach, and it does not work extremely well. It does capture some qualitative features. It does capture the fact that the sign changes, but it does not get anywhere close to the precision of the epsilon expansion in the Wilson-Fisher fixed point. And what I want to do today is to propose the following picture, and I'll try to convince you that this picture is true. So suppose you have mean field theory in 3 dimensions. So there is a renormalization group flow to the Ising model in 3 dimensions. And that has been well established. And we know lots of things about this model. This is the pure Ising model. Now, what I would like to claim is that this disordered Ising model is, in the renormalization group sense, very close to the pure Ising model. You can also get by such a flow, but it would be more convenient to go down this path. So what I will try to do is a description of this model starting from this one, assuming that everything is known about this one. So the underlying assumption is that by now we're so proficient in calculations in conformal field theory that anything of practical matter about this model is already known. And we will use that information to try to say something about this. And the tool is going to be disordered conformal perturbation theory. Now, why is there a small parameter? Okay, when we do conformal perturbation theory, we need a small parameter. And somehow nature provided us, luckily, with a small parameter. The small parameter is alpha. So what I'm going to claim is that the heat capacity exponent is a correct small parameter in such expansions from pure systems to disordered systems. So if some pure system has a small alpha, this is a claim about some perturbative expansion, and I claim that it's a rigorous claim. So if alpha is very small in some pure fixed point, small and positive, then the disordered fixed point of that type would be very close, arbitrarily close, and you could expand in alpha. So this is the small parameter. And indeed, it's 0.1. So you expect this kind of computations to be effective. So this is the small parameter. Okay, this is the idea. The idea is that you can expand in the heat capacity exponent. That's the physical idea. So there are going to be some loop computations analogous to those that were done in QCD and other theories, one loop computations. and one would try to develop this kind of formalism and then see if it yields interesting results about the critical exponents of disordered Ising systems. So let me just mention that the one-loop computation gives a result which is within 1/6. So the experimental error here is 0.1 essentially. That's more or less the experimental error. And the one-loop computation does land in the 2 sigma zone around this result.
By experiment, you mean simulation, right?
Monte Carlo simulations as well as experiments. So, for example, you could imagine that you have an Ising, like a metal or something of that sort, with impurities. So there will be some impurities somewhere. Now, these impurities do not equilibrate on the same time scale as the spins. So if the spins equilibrate very fast, then they in effect react to the properties of where these impurities precisely are. These impurities could be moving with some very long time scale, and they could equilibrate on some different time scale. And then effectively, this disorder is quenched because the impurities don't react to the momentary, to the instantaneous configuration of the spins, but the spins react to the configuration of the impurities. And such systems exist. Yeah, experimentally there are many. I don't know the names. They have these long compounds, but such systems really exist, and people measure, and it's more or less consistent with Monte Carlo. And people believe there is a more or less unique fixed point. I think it's a consensus. Maybe experts can correct me, but I think there is a consensus in the community that there is one universal fixed point which describes this random temperature Ising model, because the experiment, Monte Carlo, and theory more or less agree. Okay. Any questions about the introduction and motivation? So now what I'll try to show is that.
So you're focusing on the case of weakly random temperature.
Right.
But
Now
for D equals 3, there's a possibility, or it's believed that if it's strongly random, there's a different low temperature phase.
Right. So what I'm going to do is I'm going to describe a certain fixed point that exists for weak random temperatures. Now, if this C is extremely large, if these fluctuations are extremely large, then it would not be amenable to such simple-minded quantum field theory techniques, and then one would have to think about something else. And I agree with you that, of course, it's well known that if you make this parameter J into a totally random variable, not a random variable with a small Gaussian width, then you get a spin glass, which is an altogether different universe. It's a very different phase, very different. But I'm not going to discuss spin glasses. I'm just going to discuss weak disorder. Okay, any other questions about the motivation?
Can I ask one question? Everyone knows the answer here. But in the case of D is equal to 3 random magnetic field, where you say again you get new critical exponents, is that fixed point also close to the?
No.
Okay.
It's believed not to be close. So it's an infinitely coupled. People say it's a fixed point with an infinite coupling, whatever that might mean. I don't think there is an operational sense in which this is true, but that's what sometimes people say, and I think just from that you see that it must be very, very far away.
As infinite dynamical critical exponent.
Yeah. You need to flow infinitely long in the RGISC, to get there. Whatever that might mean. I don't know in which metric it's infinitely far away.
Well, there is an RG. Whether you believe it's fully controlled is less clear, but in a certain sense in which.
Yeah. So I think that is a very interesting system, but I won't have anything intelligent to say about it.
But do you see that if you try to use your methods on that system that they break down?
I haven't tried. I haven't really tried, but you'll see just from the get-go that since I'm doing an expansion in alpha, and the effective alpha for that kind of expansion would not be very small. So it's like a quantum field theory with a relevant perturbation. And in principle, it could go anywhere. And I won't know how to do that. There have been there was a lot of literature about that in the 80s, about emergent supersymmetry. The idea was that these three-dimensional models can be somehow reduced to quantum mechanics. These three-dimensional models with random magnetic field can be reduced to quantum mechanics by what's by the Paresis-Sourlas mechanism. But I mean, that's not true. I mean, there was a mistake in the derivation of the Paresis-Sourlas dimensional reduction idea, which is the same mistake as what we call in particle physics the Nicolai map. So the idea that all fuzzy quantum filters are trivial. So it's the same kind of mistake, and I don't think nowadays there is a controllable way to think about this. Okay, so let me start by the definition of what I'm going to do. So the definition of what I'm going to do is that what we want to compute is the free energy of the disordered system. That's an object that encompasses all these critical exponents, and it encompasses a lot of information about the disordered critical points. And those are defined as some path integral. And the idea is to try to say something about this path integral. So we path integrate over the random variable, which in my case would be random temperature. So dH. We path integrate. So, and then we have the partition. We have the free energy of the normal Ising model, which is some functional of the magnetic field H, or of the temperature H. H could be anything. And then we have an integral over H squared over 2C squared. So that's the path integral that we want to study, where W of H is defined to be minus the logarithm of the usual partition function, which is some path integral over the quantum spins with the usual action principle. And that's a functional of H, because we could add H times any operator. In my case, I'll be interested in the energy operator, which that would correspond to having random temperature. If you wanted to study random magnetic field, you would put sigma of x rather than epsilon of x. So you get some functional of H here, you plug it here, and you get some disordered free energy, which is a function of C. So, and it obeys some kind of Cullen-Zimansic equation, that when you change the scale, then you need to renormalize C, and at the fixed point C does not change anymore. So a random fixed point is a point where C does not effectively change as we change the scale. So you can extend many of the normal ideas in quantum filtering to such renormalization group flows. I don't think it has been done very systematically, but I mean, this rough idea that C can be understood as a function of the RG scale is true. Okay, so this is not a standard path integral to study because of the log. And so this is not a standard path integral, and the way we're going to think about it is by the replica method. This is going to be the approach. But I just wanted to say that some people find it distasteful to use the replica method. But for anything that I'm going to do, because there is this underlying assumption that I'm going to do an expansion in C because the disordered model is supposed to be pretty close to the pure model, it won't matter. So you can reproduce all the results by a direct study of this path integral as a function of C, and you don't need the replica trick. But the replica trick makes the computation a little bit quicker. So for me, it's just a technical tool. It's not something that I must rely on. Now, before that, let's do some dimensional analysis to explain why the heat capacity exponent is the right expansion parameter. So I want to convince you that a small alpha corresponds. When alpha is small, then you could make you can have a rigorous expansion in alpha, like we have a rigorous expansion in the gauge coupling in QCD. So let's do some dimensional analysis. So looking at that term, we can choose C to be dimensionless. It doesn't matter how you do this kind of dimensional analysis, but let's just choose C to be dimensionless. In that case, H carries dimension D over 2. And in that case, you see that whether or not this interaction is relevant depends on the dimension of epsilon. So epsilon is some operator in the theory, an abstract operator in the theory, that could have various dimensions. So now we see three cases If the dimension is bigger than d over 2, then this interaction is going to be irrelevant, and you're not going to be too much perturbed by the existence of disorder, and the critical exponents would agree with the critical exponents of the pure fixed point. If the dimension of epsilon is, so this is, in this case, it's going to be irrelevant. Now, if the dimension is smaller than d over 2, then this disorder is relevant, and it could take you anywhere. It could take you to a faraway fixed point. It could annihilate the second order phase transition altogether, and you have to do a case-by-case study. But so it's a relevant perturbation. And then there is the interesting situation when the dimension of epsilon is exactly d over 2. Okay? In this case, it's marginal. These interactions are marginal, and therefore one is prompted to compute one-loop corrections, exactly like people did in the 70s for Yang-Mills theory. So in this case, you would like to understand whether it's marginally irrelevant or whether it's marginally relevant. Maybe it's exactly marginal. Right? So one has to do one-loop computations or two-loop computations. And very little is known about that, actually. And that's going to be the focus of my talk. Because if you remember, the heat capacity exponent for the Ising model in d dimensions is given by d minus 2 delta of epsilon over d minus delta of epsilon. That's the exponent that appears when you measure the heat capacity. T minus Tc to the power minus alpha. So when this parameter is small, it means that the numerator is small, and therefore you're near the marginality bound. And it so happens that in nature, in the 3D Ising model, this is 0.1. So this is in the 3D Ising. It's just a coincidence as far as I can say, but in 2 dimensions it exactly vanishes, by the way. In 4 dimensions it exactly vanishes. And in 3 dimensions it's 0.1. So these kind of computations are relevant for a bunch of systems. Let's say, at least for the Ising model and the XY model, for any d between 2 and 4, these computations could be conceivably interesting experimentally, and there are many other systems. So there's a small parameter that exists in nature, and this is the right expansion parameter around the marginality bound. And so one is prompted to do some one-loop and two-loop computations. And this is what we've been doing with David Simmons-Duffin and John Carley. So I'm going to present some results. I will only sketch the derivation. And then I'll write the key formulas. Are there any questions about this point?
So if alpha is exactly 0 in 4 dimensions, can you use the same? Is this technology useful there?
Yes.
We've hopefully so far explaining why 3 dimensions is interesting, but what is the 4-dimensional Ising model understood in this context?
That's right. In the 4-dimensional Ising model, the 4-dimensional pure Ising model is a mean field theory. So this is somewhere here.
Oh, I see.
Now it's mean field theory, and it's marginal. It's marginal indeed, and people have done some perturbative computations for this order in that case, and they found this singularity which renders the epsilon expansion ineffective. Because let me just explain why. Just 1 second. So this is a marginal perturbation in 4 dimensions,
Okay.
but there is another one, which is just epsilon squared. And so in 4 dimensions, you have to study a 2-dimensional space of RG flows, which cannot be mutually disconnected. They are not disconnected. And the determinant or the discriminant of this 2 by 2 matrix has a 0 of some sort, a singularity of some sort. So this leads to some singularity in the epsilon expansion. So you can study a lot, you can study the system a lot, but it appears to be not very effective in describing this 3D Ising model, because from the get-go you have a 2-dimensional space of things that can flow, and you have to understand how to connect that to 3-dimensional physics. In 3-dimensional physics, there is no epsilon squared, and that will be key. So in the pure Ising model in 3 dimensions, there is no such thing as epsilon squared. There is no operator of dimension 3. There is an operator of dimension 1.5, but there is no operator of dimension 3. Epsilon squared doesn't exist as a local operator in this 3D Ising model. In 2 dimensions, epsilon squared just vanishes identically by the fusion rules.
Actually, I have a question about that, because in principle you can sit at the clean Wilson-Fisher fixed point in 4 minus epsilon, and then this lambda squared operator becomes irrelevant.
Yeah, but then you'll have an order of limits question, because the disorder will flow. and it will be of order epsilon.
I guess what I'm saying is that you could just, I don't see any advantage to this, but in principle you could sit at that CFT defined that
You
way
can do that.
and redo the same.
You can do that. That would be analogous to what I'm doing directly in 3 dimensions. But the strengths of the disorder in this system that you're describing would be of order epsilon. So you won't be able to take, I mean, there will be 2 small parameters and they will be of the same order. So you'll get back to the previous problem. What I'm doing is going directly at 3 dimensions. And I'm just going to compute. I mean, the main substance of what we're doing are these perturbative computations for marginal disorder that have not been done for d bigger than 2. So that's what we've been doing. So I mean, it's really just one-loop computations in these kind of systems. So the main first. The replica, as I said, the replica is not absolutely necessary, but it's something that we do. So we can define something that we call Wn, which is defined as the following path integral: dh z to the power n of h e to the minus h squared over 2c squared. So we just define this object, which contains the partition function to the power n of the pure Ising model, weighted against this exponential, and there is always an integral here. And then the disordered free energy can be obtained from those by a derivative at n equals to 0. Okay, so if you could solve this, then you would be done. You need to do some analytic continuation in n, but if you could do this analytic continuation in a way that you trust, you would be done. For me, this is not. I mean, these analytic continuations always exist because I'm going to do an expansion in c squared. So all the dependence on n will be polynomial. There will be no ambiguity with analytic continuation, and you can convince yourself directly that this perturbative expansion in C is in 1-to-1 with a direct perturbative expansion from the defining path integral. So there is no doubt that in this situation there is no replica symmetry breaking, or none of that happens. It's a straightforward generating functional for perturbative diagrams. Anyway, so the idea is to solve this for integer n, and then do some analytic continuation. So how do we do that? For integer n, this is a standard quantum field theory. That's the virtue of the replica trick. That's why the replica trick is so popular, because it converts these hard problems into problems that look more amenable to quantum field theory tools. So Wn can be understood as a path integral over the spins of n copies of the Ising model. So we now have n copies of the Ising model, where a goes from 1 to n, and then a path integral over h of the following action. So now it's a standard action principle. You have n copies of the Ising model completely decoupled. They all talk to the same external random field, but they're still completely decoupled. And then there's h squared over 2c squared. Okay? So this is Wn. It's a standard quantum field theory. You can integrate out h straightforwardly, because now h appears in a quadratic fashion. And this becomes d sigma a going from 1 to n, and then e to the minus sa plus c squared over 2 sigma a sigma b over all the replicas. Okay, so that's a straightforward computation. And now there is an interesting subtlety that makes 3 and 4 very different for some applications. You can still compute many things about 4 and many things about 3, but you have to treat them differently. So notice that we have now n copies of the Ising model, and they talk to each other via some composite operator, sigma a, sigma b. But you have to make sense of this operator when a coincides with b. So, and at that point, the discussion of theories that are large n or free fields, like in 4 dimensions, is very different from what I'm going to do. Because in the 3D Ising model, so if you were to discuss some large n theory, where epsilon a is a single trace operator, or if you were to do some in-field theory, then you would have to keep these operators, because they're well-defined local operators that they do not cause well, that do not, these are marginal operators. That's what I want to say in so many words. So if you are talking about large N theories or mean field theories, then epsilon A is a well-defined marginal operator. Recall that I'm assuming that epsilon has some dimension which is very close to d over 2, because my final goal is to compute some one-loop corrections to marginality. So I want to find whether it's like in QCD, that it's a flowing to strong coupling, or whether it's marginally irrelevant and it flows to weak coupling. That's what I want to find. It's not known. Okay, so epsilon A is well-defined marginal operator. That's what I have in mind when epsilon has dimension very close to d over 2. But if you were to discuss the 3D Ising model or the 2D Ising model, then there is no such thing as epsilon A, because the operator product expansion of epsilon A with itself does not contain an operator that is nearly marginal. So we have to dispose of these terms. So you can think about it as if they were to induce some non-universal corrections to what you call the absolute energy of the model, or what you call the Curie temperature. But they are not going to be important for the critical behavior of the theory, or the critical exponents. They could maybe shift the Curie temperature or the total ground state energy in some way, but they won't do anything other than that. So for the application that I'm interested in, I'll have to sum over A not equal to B. And the computations for theories in which there are double trace operators or mean field theory computations would be different, and it would change very significantly the conclusions. So I'm going to conclude that something is marginally irrelevant, and in those cases, we have done those computations, and the conclusions are opposite. So double trace operators play an important role in this business, surprisingly, perhaps. Be careful about that. Okay.
So, sorry, just to, I'm not sure I understand exactly. So I guess I would think that epsilon basically has no symmetry. So if I fuse two of them, I can get epsilon back.
Not in 2 dimensions. In 2 dimensions, there is a Cramér-Svanier duality,
Okay.
which takes epsilon to minus itself.
But 3D.
So in 3D, if you do 2 epsilons, you can get 1 epsilon, but a single epsilon is a relevant operator,
Yeah.
and it's not marginal.
But
Those that
would
I'm
I
keeping,
worry that would I need to take that into account?
Yeah, you would.
The correction to nu, for example. It sounds no.
No, that would just shift the temperature. So indeed, you could have some terms that look like some quadratic divergence. Sorry, it would be. Yeah, you could have some quadratic divergence times epsilon, let's say, in 4 dimensions. But that you could just swallow into a redefinition of what you call the critical temperature. All these critical properties like nu, alpha, beta, gamma, they depend on properties of the conformal field theory. So you just tune to the conformal field theory. And this tuning corresponds to just setting the external parameters of the system so that your long-range correlation functions.
This order times this order is ordered, so in some sense it's not really coming back to itself.
Right.
Yeah, it's not coming back to itself. Sure.
Yeah. So yeah, it's very important. And I mean, the question of whether you sum over all the copies or just A not equal to B has a very important effect on the final conclusion. I won't have time to discuss that. I just have 8 more minutes. So you can compute the beta function for C-squared. I'm not going to. So we assume that that such double trace operators.
Okay, sorry. Yeah, I'm understanding. So that's not part of the RG. That's just keeping some term.
This is what you need to tune to get to the Curie temperature.
Yeah, I'm just thinking in my mind about the condensed matter style Epsilon expansion, where to get the correction just for usual Wilson-Fisher fixed point, you actually there's a tadpole diagram. You just take the 5/4 term and do one contraction, and that renormalizes the temperature.
But that just tells you how to tune to the fixed point. It's not part of the critical exponent.
I mean, it depends a little bit on the scheme, I guess.
Yeah. If you wanted to compute the effective dimension of Wilson
scheme that actually gives the order epsilon correction to nu.
Yeah, it depends on the subtraction scheme and stuff like that, but eventually it doesn't matter. And so you can compute the beta function of c squared for any n. Okay? You can have an analytic formula for the beta function of this coupling c squared for any n. How do I do that? Well, what you need to do is conformal perturbation theory. So you have some marginal operator that connects n otherwise decoupled conformal field theories. And what you need to do to compute the beta function is to study the OP of this operator with itself. And so the computation that we do is we compute epsilon A, epsilon B times C naught equal to D, epsilon C, epsilon D. And what we're looking for is a term on the right hand side which has 1 over x to the power 3, which is what you need to get the log singularity. And then we need to compute epsilon F, epsilon G. There cannot be anything else because there is no other marginal operator that's invariant under the permutation symmetry. So you must get something that's invariant under the permutation symmetry between the copies. And that's the only marginal operator that has this property. And all you need to do is to compute this coefficient. And that would be your 1 loop beta function. Now, when I initially started doing that, I did a mistake. I forgot one term. But now let me just do it correctly. So there are 2 types of contributions to the right-hand side, which is interesting. One comes from... So what's the assumption? The assumption is that in the pure Ising model, this is the algebra of the pure Ising model, we have the unit operator over 1 over x cubed, because I'm assuming that epsilon has dimension arbitrarily close to d over 2. So there is the unit operator with x cubed in the denominator, x to the 6 in the denominator, and then there is some coefficient c epsilon epsilon epsilon, which is a property of the pure Ising model that we might hope that we know from experiment or Monte Carlo. And then there is 1 over x cubed. And there is nothing at order 1. The next thing is of order x to some power, which is positive. So I'm using this underlying algebra for the Ising model to compute this coefficient. And there are 2 types of contractions.
You mean there's an extra epsilon here?
Oh yes, of course, thank you. Okay, now you need to know this. Let me just mention that this coefficient has been measured by Monte Carlo people, and it's more or less square root of 2. They have a pretty big error actually, but David Simons-Duffin managed to decrease the error with some numerical techniques. So there is a pretty big error, but it's more or less 1.4, which is actually the average between the 4-dimensional value in mean field theory, which is 2 times square root of 2, and the value in 2 dimensions, which is 0. So the average of 2 times square root of 2 and 0 is more or less that. Okay, so there are 2 types of contractions. One is when you combine 2 epsilons when a is equal to c to the unit operator. And another is something that looks like a quantum thing, when you have a double contraction. And you pick up an epsilon when a is equal to c and b is equal to d. And you have to do the combinatorics of these 2 types of contractions. And the final answer that you find is that this coefficient is 4 times n minus 2. Plus 2. Then there is this coefficient c epsilon 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 squared. So there is a correction to the beta function that looks like the OP coefficient squared. Okay, so this is some little combinatorics, and that directly reflects on the beta function. So the beta function for c squared is just given by minus c to the 4 over 4. This is the 1 loop beta function. 4n minus 2 plus 2 c epsilon 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 squared. And then there are corrections of order c to the power 6 that you could imagine are small in these applications because of this picture, underlying picture. But we're working on computing them. Okay, so we now plug n equals to 0. That's what corresponds to the disordered theory. So let me denote it with a superscript d. So the actual beta function in the 3D Ising model is given by minus c to the 4 over 4. We plug n equals to 0. I'll flip the sign, and I get 8 minus 2. So it will be 2 minus c epsilon 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 squared. Unless a half. 2 minus a half c epsilon epsilon squared plus further c to the 6. Okay, so now you have to look at the measurements, right? The measurement says that C is more or less square root of 2. So C squared is 2. So this is 2 minus 1. So this is positive. Okay? In the 2D Ising model, this vanishes because of Cramer's-Vanier duality. So it's also positive. In 4 dimensions, you can't use this formula because I have neglected double trace operators. And something very nice happens when you include them. These 2 cancels. The double trace operators exactly cancel the 2, which is the source of these difficulties with the Epsilon expansion. So this is bigger than 0, and so it's marginally irrelevant. So the picture is that this order decays. Okay, and you go back to the pure fixed point if you're exactly at the marginal point. But we're not. I mean, in the pure Ising model in 3 dimensions, the dimensionality of epsilon is not quite d over 2. So the dimensionality of epsilon is actually 1.41, which is very close to 1.5, which is d over 2, but it's not quite. So we have to add a small correction, just like in Wilson-Fisher. So after adding this small correction, we get that the beta function for C squared, and that's the final answer, is minus d minus 2 delta epsilon. That's the correction that you could interpret as a 3-level correction. And then there is plus C to the 4, 2 minus a half C epsilon 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 squared. And that's your final answer. Yes?
You set n equal to 0. You're calculating the beta function for the n equals 0 theory.
Yes.
Where are you taking the derivative?
Oh, that's a great question, which I skipped intentionally. So let's consider the passing. You see, this is the path integral. So there are 2 sources for dependence on n. Where is the path integral that I want?
Well, that's it.
Yeah. So to explain the answer, I'll just need to write one more formula. So we have integral of dh, z to the power n of h, e to the minus 1 over 2 c squared h squared. Okay, this is what I start from. This is just that. Wn. Now, C changes as you change the renormalization scale in a way that depends on n. Because this is the number of copies. And there is an n here. What you need to take a derivative of is this thing, and then set n equals to 0. Now, your derivative could hit either that n or that n. If it were to hit that n, and you would have plugged n equals 0 here, you would get nothing. So the derivative cannot hit that guy. It must hit that guy. And then to compute the beta function, you just plug n equals 0. Okay? So the beta function for C squared is just obtained by plugging n equals to 0. So this is the final answer. And now you just plug numbers that are experimentally more or less measured. There is a perturbative fixed point, which is very close to the pure, which is with a very small C squared, because that number is very small. So what you find is that C star squared, this is the strength of this disorder at the fixed point, and it doesn't change as a function of the renormalization group scale. It's d minus 2 delta, and then there is some denominator, 2 minus a half c squared. And that's a small number. If d is very close to 2 delta, this is much smaller than 1. So your disordered fixed point is very close to the pure fixed point. And now you can compute anything you want about it. Okay, so this is the proof of this claim that I made in the beginning, that under some conditions, what are these conditions? The conditions are that there are no double trace operators. And the second condition is that the OP coefficient is not too big. If the OP coefficient were too big, then this would be like the QCD coupling, and it would run to strong coupling. But if the OP coefficient is not too big, and I in fact don't know of any theory where this OP coefficient is too big, then it's marginally irrelevant. If there are no double trace operators, and if the OP coefficient is not too big, then it's marginally irrelevant. And then there's a perturbative fixed point, which is completely controllable, and you can compute its heat capacity. You can compute anything you want about this fixed point, and the final formula would be the heat capacity in this fixed point, which you can directly contrast with experiment. So the heat capacity of the disordered Ising model in this one loop approximation, after some algebra, you find that it's delta epsilon minus d over 2. And that's the prefactor. And then you have 2 times the OP coefficient squared over 2d. No, that C epsilon squared. Okay, that's a formula that's at the one loop approximation is valid for all theories of this sort. So you can apply it to many theories. 3 interesting conclusions that you can derive from this formula. One is that alpha is always negative, because this is negative by assumption. You have to. This is what triggers the RG flow, because you have a marginally irrelevant one loop contribution. So the tree level dimension has to be slightly positive. So this is consistent with this theorem that you mentioned. So it's always negative. It follows from the one loop approximation, because this is manifestly positive, and this cannot change sign, because if this were too big, then in fact the whole computation there would break down. And you can show that the condition for this not to be too big is exactly the same as the condition for that not to be too big. Okay, so this is always negative. If you specialize to the 2D Ising model, then the numerator vanishes because of this duality. And you find alpha dim, so I should have said maybe this, alpha dim equals to 0. And that's exactly what experimentalists have measured. That's exactly what was measured in experiment. In the 3D Ising model, you just plug numbers, and you find that alpha dim is more or less minus 0.12. Which is well in the right ballpark. And you can repeat this kind of computations for many other theories, large N theories. We've been considering the Heisenberg model in various dimensions, various large N theories, applications to ADS, and many, many things of that sort. I just wanted to make sure that it's clear that once you have double trace operators, many of these conclusions change. But you can adapt. You can do. So this is just an example of one thing you could do pretty easily. And this is just alpha. You can compute nu, alpha, beta, gamma, and they all work pretty well within one or two sigma.
You just look at operator insertions in the epsilon correlator or something?
Oh, you're asking how would they do that? They compute 2-point functions of phi squared and phi squared in the Epson expansion. That's one thing you could do.
How you get it?
Oh, how I did get?
You got the fixed point value now. And
yeah, and I convinced you that it's a weakly coupled fixed point, so you can imagine that I can compute anything I want about it. I didn't explain how we did that, but this is the final result of some computation.
In the specific heap, there are logarithmic corrections?
Yes, indeed. In 2 dimensions, it's marginal, and you can compute these logarithmic corrections, including the coefficient, and you can contrast with the experiment, and it works.
It's double log.
Yeah, it's double log, in fact. Yeah. You can contrast and it works. So you can do lots of things of that sort, which this is just one example. And now one of the things that we're trying to do now is to complete the 2-loop computation, because without a 2-loop computation, you don't know what's the error on the 1-loop computation. So we're doing the 2-loop computation now, and it's probably going to be done at some point.
That will involve other things you have to get from the lattice.
Well, at the 2-loop level, you get a 4-point function. You need to know some integrated, connected 4-point function in the pure Ising model. But we know that. I mean, we can plug all the low-lying conformal blocks and approximate it in all the regions where there is a nice OP. And yeah, we know it to pretty good numerical accuracy. Probably exponentially good numerical accuracy.
Also, aren't the A equals B terms going to feed in? That is, in the OP, I mean, they're not close to marginal, but they'll feed. I mean, don't they?
Well, you have to somehow concoct a 1 over x cubed on the right-hand side.
Mm-hmm.
So
that they don't give a systematic variance.
No. I mean, at the next order in perturbation theory, you need to integrate a 4-point connected diagram.
Yes, that's the same. Good.
And everything enters.
Good.
But we know how to approximate this 4-point function by inserting the few low-lying conformal blocks. And it's an exponentially good approximation.
Mm-hmm.
So, yeah, in the end of the day, all the operators fit in. But you can write a closed form formula for what you need to compute.
Thank you for a fantastic talk.